We are now on to section 1.2 in our text, which is about patterns and problem solving. 1.1 was the problem solving aspect. And now we're going to look at patterns because patterns uh, really play a significant role in mathematics, observing patterns. These occur in many different fields. Psychologists analyze patterns of human behavior. Meteorologists, recording this in early January in Michigan, and so we know about meteorologists help observe patterns in the weather, astronomers observing patterns in stars and galaxies, detectives identifying patterns and clues, mathematicians then study patterns to devise algorithms, right? Things that are used in computer science to describe problem-solving processes. And so patterns is really at the heart of mathematics. And so we have to learn how to identify those, how to continue those, how to prove that a pattern might hold over a certain time. And so let's take a look at what our important terminology is going to be in this section and what are the main things we're going to be talking about. So we are going to start with an introductory problem. We will talk about patterns, which will lead to sequences, numerical sequences. There are many different numerical sequences and patterns, famous ones that we'll talk about, including the Fibonacci numbers, Pascal's triangle. Maybe you've heard of those before, maybe not. They're pretty fascinating. Things called arithmetic sequences and geometric sequences, triangular numbers, finite differences, and then we'll get into something called inductive reasoning, and talk about counterexamples. And then in the last section, we talked about problem solving strategies, and we'll look at one more, which is solving a simpler problem. So what I'm going to do here is start off with another introductory problem, something I would love for you to pause the video once we start this and have you try, because so much of your learning in this course is about you trying things and seeing how your own brain works. We talked about that in the previous section. Your metacognition, thinking about how you were thinking. That's going to allow you to then understand how others will think about the same problem or similar problems. And so the introductory problem. So here's a little intro. And maybe you've seen something like this before. It's a matchstick problem. So if you've got matchsticks, or maybe toothpicks work great for this sort of thing. Maybe even pencils or pens or something where you've got little sticks, right? And crayons. I would suggest that you again pause the video, get those, and try this. And so the way this works is you are going to take four of those, well, I'll just say matchsticks, and create a square, okay? And then you're going to build more squares. So just a big, long string of squares, a big track of squares, one after the other, okay? And we'll just start with four of them, okay? So I'll draw four. All right. So the question is, how many matchsticks? That's the question. How many matchsticks does it take to make a given number of squares in a track like this? And so if we even go back to the beginning and just say one square, how many matchsticks does one square make? Well, that would be four, obviously. One, two, three, and four. If I make another one attached to it, what are we up to then? 1, 2, 3, 4, 5, 6, 7, right? Because we added these three. If we make a third, now we're three more. So we're at 10. And then to make the fourth, again, we have three more. So we're up to 13. So the question is that I have for you, again, play with these, use the physical representation, is how many would it take to make 60 squares? And you may not have enough matchsticks or toothpicks to do this. So what you need to really do is come up with some sort of generalized pattern, right? Can you come up with a way to or observe some pattern where you could predict uh, or calculate without just counting every single one how many matchsticks it would take for 60 squares, or any number, right? Or any number. We'll just call it n, right? Any number of squares. So I suggest you pause and try that problem out on your own. I'll keep going here to kind of show you how you might think about this. And there's never one single way, right? We talked about the process of problem solving before. And so one of the things, we've got the picture, we've got the manipulatives. One of the things that we might have noticed is that, again, to go from one to the next, we're always adding 3, right? Plus 3, plus 3, plus 3. So you might think, well, can we just take the number of squares that we have and multiply it by 3, right? Does this work? Is this a possibility for calculating our answer? Well, if we look at the problem that we just did there, 4 squares times 3 is equal to 12. 4 times 3 would be 12. And we said that the fourth had 13. So the actual number of squares was 1 bigger than what we had here, right? It was an additional plus 1. Well, so does that help us, right? Does that help us? Well, let's go back and say, well, let's try out a different number of squares and see what happens. Let's say we just start with, let's go back to 3. Let's go back to 3 squares. 3 squares, let's do the same thing, times 3 gives us 9. Well, what was the actual number of squares? 10. So that was also 1 bigger. What if we go back to just 2 squares? 2 squares times 3 is equal to 6. What was the actual number? 7. We're starting to notice a pattern, right? If we take the number of squares that we need, multiply it by 3, and then add 1, is that it? Adding 1? Does that give us the total number of matchsticks? I think it does. And you can sort of see that, right? Even if you draw this out differently. So the way you might draw it out is think, all right, for the first square, I've got 3. For the second square, I've got another 3. For the third square, I've got another 3. And every other square is going to have another 3. But then you've got this one starting matchstick at the very beginning. So if you think about it like that, here's the 1, here's 3, here's 3, here's 3, and here's 3, right? And so if you wanted to know how many would be in 60 squares, well, we could take 60 squares times 3 matchsticks plus that 1 additional matchstick. So that's 180 plus 1. And we can predict that there would be 181 matchsticks in that string of squares. And so this pattern-based problem-solving approach kind of connects with the stuff we talked about in section 1.1, that problem-solving section. So what we're going to transition to now is to specifically looking at patterns, different types of patterns. Many of them will be numerical, but we're gonna and we'll start with a simple numerical pattern, and then we'll talk about other patterns too. So a pattern. Let's examine these numbers. I'm just going to give you a list of numbers: 1, 2, 4, and 8. And I say, can you tell me what the next 3 numbers would be in that pattern? And so just, again, pause, fill in the blanks. What are the next 3 numbers in that pattern? Well, when you see a numerical pattern, how do you determine what the next numbers would be? You have to make some observations, right? Can you make some observations about how we get from one number to the next, to the next, to the next, where we do a repeated thing every single time? And what you may have noticed is that each time we are doubling the numbers. 1 times 2 equals 2. 2 times 2 is 4. 4 times 2 is 8. And so we should be able to then continue that pattern. That's one way that we could solve this problem. 8 times 2 is 16. 16 times 2 is 32. And 32 times 2 is 64. So this would be a numerical pattern, right? It's a numerical pattern. We observed something happen with numbers. But many people like to see things first when they're starting to learn about patterns. Not everyone is developed, especially at a young age, that elementary age, that number sense, that ability to sort of see numbers. And so introducing something as a numerical pattern might not be the best way to even introduce the idea of patterns. So maybe we start with some sort of visual pattern, some sort of pictures. So what I'm going to do is I'm going to draw a few different pictures here. And your job, once I draw these, will be to continue the pattern. Draw the next, let's say, drawing the next three pictures in the pattern. Okay. And so I'm going to shade in a few things here. And again, pause the video and draw out the next 3 figures in the pattern. 1, 2, 3. So pause, make some observations, and then draw those. All right. So I will continue again. So what we noticed here in this visual pattern is that we had these squares, right? We had these squares, and they were cut up into a grid with 4 sections. And each one of them had a shaded section. And the first one was shaded here, right? So the first one was shaded here. The second one was shaded here. And the third one was shaded down here. So 1, and then 2, and then 3. So can we presume then that the fourth one would be shaded down there? I think so. So our fourth one should be shaded down here. And then if we're going to assume this pattern continues, then we would reasonably, right? We can reasonably assume that we would then just keep going and reshade back in this first position here. It's almost as if the shading moves clockwise around the circle, right? Or around the square. So 1, 2, 3, 4, 5, and then we start back again with 6, and 6 would go here. So that's a good example of a fairly simple visual pattern, shading in different geometric figures. Now, you don't even have to have numbers or pictures to represent a pattern. This is a fun one. You can even have word patterns or name patterns. We'll do a name pattern. And so I'm going to list 4 names. I'm going to list 4 names. Al, Bev, Carl, and Donna. And your job is to determine what is the next name in the list of names here. So pause, determine an appropriate next name for this. I'll keep going. So as you looked at this, the first time I saw this question, this pattern here, the thing that jumped out to me was the first letter in the the names A, B, C, and D. That was the first thing I observed. And so I said, well, the next one has to start with an E. I said, okay, well, the next one has to start with E. But then I also noticed that the names got a little bit longer. And so I said, oh, well, the first name has 2 letters, the next has 3, the next has 4, and the next has 5. And so I said, well, you could come up with then some 5-letter name that starts with the E. What I didn't notice the first time I saw this, though, until I read the response, was that there was another pattern. Did you notice another pattern in this list of names? The names alternate between what would be traditional masculine and feminine names, right? It alternates. Masculine, Al, feminine, Bev, masculine, Carl, feminine, Donna, right? So these sort of traditional masculine and feminine names are alternating. So if we also adopted that element to our pattern, we would need a 5-letter name, 3, 4, 5, that starts with E, and that had a traditional masculine held a traditional masculine name. So it could be something like maybe Edward. I said 5 earlier. It needs 6 letters. I was like, something's weird. Maybe Edward, Eugene, Elijah, Elliot. Edward was the first in my list. So there are lots of options that could be the a correct answer for that one. But it really depends on your own observations in that case, right? Sometimes there may be maybe more than one appropriate answer. It's just really important to note for this introductory video that patterns are really everywhere. Often there are patterns we don't even see. And we are going to talk about in the next video different types of patterns, specifically sequences that things that show up in nature, things that often inspire mathematical discoveries.